Yaskawa.
Hello everyone, this is Yaskawa America. This is Kevin Hull of the Applications Engineering Group. I'm here with Greg Finley and Nishant Unikrishnan, and thanks for coming to the webinar this morning. Today we're going to discuss there's three separate but related topics we're going to cover, so it's going to be an interesting webinar. We're going to talk about CSV file transfer and some function blocks to read data into the IC application, and thirdly, we're going to talk about creating XY interpolated motion paths. So these three separate topics will be discussed in terms of how they can be used together to solve an application this morning. And first of all, I'd like to have Greg Finley begin and discuss some work he's done recently regarding the creation of a program to send data files to an MP2000 IEC controller. So at this point, I will hand it off to Greg.
Hello, everyone. We want to discuss about getting your file over. I mean, everybody knows about the Modbus TCP and Ethernet IP communications method with the IEC controller. Well, a simpler way to transfer just a file with all your data contained is using the controller server to transfer your information. Some of the uses we found currently in applications that we're doing now are people are using this for recipes, part files, paths such as gantry robots, and machine setup are some of the application uses that we've seen so far, people using this methodology to have a file to describe the machine setup or paths or parts being made on a machine with the Yaskawa controller. I just want to give you a little bit of overview of the procedure for transferring that. You use the Ethernet communications to transfer the information to the controller. The IEC family built-in server makes this possible and quite simple. What I personally used is the HTTP protocol that sends a block of data with the request. For people that aren't familiar with the HTTP protocol that's used in your email service and stuff, it's quite well documented on the web. And it's quite simple. It's basically wrapping the request around your data that you want to send over. One of the simplest ways with Microsoft and the frameworks version of Microsoft is using the HTTP web request class and using the post method of the HTTP web request class to transfer the file. The two places you can put the file on the controller is either to the flash by putting it to the flash user data directory, or RAM disk, which is the RAM of the memory, which will lose that file on power toggle. So one of the methods of what we've used so far is using some C# code where we pick the IP address, and we're using a built DLL to transfer the file to the controller using the HTTP web request. Some of the code, for example, when you're using the HTTP web request, is you pass to this class. You will pass the method of the request, the URI of your resource, which would be the IC controller in this case, and then also information about the protocol, such as the content type, the headers and then the actual data. Just a brief overview, just to help simplify the understanding of an HTTP request. The HTTP request usually consists of 3 or 4 parts: an initial line, the header lines which could be multiple lines, and then the optional, which is the message part of your header. So in your initial line of a HTTP request, you state the method, which in our case we recommend the post, and then the local path of the requested resource, which is the IC controller, and then the version of the HTTP protocol. In the case that I've used successfully is HTTP 1.1 for sure works. And then in the header lines you discuss the details of the content type. In the case of a CSV file that we've transferred, that's a multi-part form data with a boundary, cache control, no cache, and then your host IP address and directory location, whether it's the RAM disk or the flash, and then the content length in bytes, and then the connection type is keep alive, so you don't get a timeout, and then the multi-port form data, and repeat the boundary is the MIME explanation part of the header lines. MIME is a leftover from internet mail, but it's also used in HTTP protocol. And then the optional part is the message where we actually put in bytes, we stream the data over to the controller when it's wrapped with the HTTP protocol. And then as if you do a write to the flash, you would be able to observe that in the, once you logged in as the administrator, you'd be able to observe that under the user data. In the case of the file that we're going to talk about today, the CSV file racetrack has been put into the user data that you would be able to see in the archive to confirm, maybe when you first initially start debugging your application, to confirm that you've successfully written over to the controller. That's kind of a brief overview of the methodology. Let's say we use .NET with the HTTP web request, or I've also seen it done successfully with people used Excel with the WinHTTP web request component, which is an ActiveX object. That's also a successful method I've seen used. My recommendation probably is using the Microsoft environment because it's quite simplified, with letting the compiler and operating system with frameworks do most of the work for you. With that, I'd like to turn it over to the next section, Kevin Hall.
All right, thanks, Greg. I think those tools you talked about were a nice alternative, or additional method to automatically send files to the controller, because obviously you can do that through the resource download box. You can send a file to the controller. You can also send a file using the hardware configuration, but for an automated system that has a PC, HMI, or other device, it'd be nice to send these files that you're talking about more at runtime while the machine is in production on the factory floor. And that's kind of the overall part of our discussion here, where we're going to talk about the XY interpolation paths coming up, where you might need to send that data down on a daily or a weekly basis based on the part the machines are making. Okay, so once those files are sent to the controller, you still need a way for the IEC application to be able to take that data and use it. And that's the next section we're going to talk about. This is the file read-write template we've been working on. So this is kind of the introduction to this, this new set of application code we are developing for sharing with you. We call this a template instead of a toolbox because in all cases this will require customization based on your application. You'll have to customize the data types and the structures based on the file you're trying to read. So it's not as maybe turnkey as the other toolbox projects we've put out to date. And basically this template builds upon there's 7 function blocks available in the Prokonos firmware library that are shown at the left of the screen. And those are very basic functions for doing some file manipulation. And so we've kind of containerized those into some more higher level functions to add more functionality. Okay, so some of the other functions we've added, let me just kind of give you a little overview. As Greg mentioned, you can use a VBNet or C#, some kind of a tool to send the file down to the controller. The other alternatives that are less flexible are through the web server, hardware configuration, etc. And to get it into the file system of the controller. And the piece I'm discussing now with the file read-write template is how to get that data into the IC application. And then in contrast, you can go the other direction as well with this file read-write template. If you want to read files out of the controller, it's kind of a reverse process, and there's function blocks for that as well. You might store part data or alarm info or any kind of data into the file system of the controller and upload that at a later time. So here's some of the purpose for this template and the benefits. So you can send and receive a wide variety of complex part recipe data, and I think it lends itself more directly to doing that than the other communication protocols available, because Modbus, Ethernet IP, and OPC are are more designed for a cyclic set of data with a refresh rate, and it's a little more difficult sometimes with the Modbus registers to represent a more complex set of part data that might not be represented so well in a register. It might be an LReal value that you'd rather use as the native format. So this kind of bypasses all those protocols, and it's a completely separate thing that you could download this file once and have that data in the controller, or just download it once a day or whenever that data needs to change. And you also don't need to worry about any Modbus registers or IEC addresses to locate the information at. So some of the capabilities, we can do binary files, you can read or write those, or a CSV file, which is basically the ASCII character representation of all the data values. And that's probably a more user-friendly or more easier file to read and discern or edit in Excel or to view in Notepad, because it's going to be native to the human being who's reading it. But the binary files are more compressed typically, and also aren't intelligible unless you have a program to decipher what the data was originally. We've put in provision in the function blocks to optionally store a version data in the file so that multiple versions of the file could be understood and deciphered by the function blocks and converted to the user structure in the IEC format. And additionally, you can pick what kind of a delimiter you'd like to use with the CSV file. So it can be a tab, it can be a tab, it could be a comma, it could be a semicolon, and that's available as a function block input, as shown here on the read CSV file. This slide shows a little example of what the CSV file could look like. This is one of the files we've been working on, and it had, well, through the development, it had a range of different file formats, so that this was kind of the reason we wanted to put a version control system in there. It ranged from, I think, 22 columns to 44 columns before it was done. So this particular example is in total 44 columns of data. And the very first row, we use that cell as the version code. And we use a date code, so that means 2011. And then it says 0519 if you can't see it. So we just simply flag it as the date that spec was created. So now that we've had 44 columns, we know we did it. And if we see that as the first field in the file, we know how to read the file. And the lower half here of the screen kind of just shows a snippet of the read CSV file function block. And we've kind of tried to comment where the customization has to take place and to add some cases to identify the different version codes so that the file can be dealt with properly. And here's another snippet of that same function block, and these would be the two pieces that you would have to go in and customize. So this represents a case statement where each of those 44 columns is read and converted from the string data, the CSV data, into the actual data type of the structure to be used in the IEC application. So you can see kind of down the center here a bunch of string to LReal or string to DINT conversions of the CSV's value as we parse through the file. And this slide just kind of shows a collection of information that you would be dealing with if you were using a binary file system. And this one shows the controller itself writing binary data to the file system. So to start with, we got some IEC structured text at the top here, and we're just loading a structure with some test data. So here's a for loop. It's got 101 elements in it, and we're setting each element to a specific number. And you can see that if you look at the data in the watch window. So here was the version code, very first 4 bytes of data, set as mydata.version. And then the first couple of records are shown here, and you can see the values 1, 2, 3, 4, 5, 6. Now it's interesting to note that we're only setting the first 6 elements in this for loop, but actually this mydata structure is defined to have 8 items per record. And so you can see that they're unset. They're just zeros from initialization. Okay, so now this file was written to the controller's file space. And if you uploaded the archive.zip, and if you looked at the contents of the file as we show on the bottom half of the screen, this is a utility program called UltraEdit, just for viewing the byte values of a file. You can kind of look here and see the actual data from the file. And it's not clear at first, but the first 4 bytes are the 4 byte of the version, and they are in backwards order. So if you were to use Windows Calculator and go in hex mode and punch in 01 32 B7 A3 and then convert it to decimal, you would see this number, the date code. And part of the way the function block writes a file is the next step is to write the number of records that follow as a check for the reading system. So the next 2 bytes contain the number of records to appear, and this is 0065. And so if you convert 65 from hex to decimal, it'll be 101 records. And then the actual data follows. So you can see the 01, the 02, the 03, which repeats for the 101 records. So in summary, this file read-write template is still, we've been developing and experimenting with this for most of the year, just to kind of make it useful for the applications and do some testing and some just exploration with what's possible there with those Prokonos firmware function blocks. And so far we've actually used it in one application as it is here, and we've used the Prokonos file handling function blocks in 2 other applications. That was earlier on before we decided, hey, this would be a great thing to kind of convert to a template for easier reuse. So right now we're really still, I think, in a beta phase with this and looking for applications that could benefit from it and do further testing and further explore the capabilities. And we would be looking for feedback on this as well. Okay, so that concludes the first 2 parts of the webinar of getting file data into the IC application. And so next up will be Nishant, and he will discuss how that data can be then used to make some motion.
Thank you, Kevin. Hello, everybody. So far you've seen from the previous 2 presentations, you've seen how you can basically transfer data from your PC into the MP2000 IEC controller, and once it's in the flash or RAM of the controller, once it's in the memory of the controller, you saw from Kevin's presentation how you can make use of some of the function blocks that we are developing to bring this data up into the application so that the data can be used and motion can be created out of it. Today, this what we're going to see now is basically a discussion on 3 function blocks that have been created in the Gantry Toolbox. The Gantry Toolbox version 8 for MotionWorks IEC 1 and Gantry Toolbox version 200 for MotionWorks IEC 2.0. The 3 function blocks are Path Generator, Move Path, and Calculate Angles. Let me give you a brief motivation to why we decided to create these function blocks and this functionality with the IEC controller and with MotionWorks IEC. While we're waiting on the development for Part 4 of PLC Open, which deals with interpolated motion, a lot of requests and a lot of interest was being generated on how to do coordinated motion. Not exactly interpolated motion, but coordinated motion for XY axes or XYZ axes for simple applications like path following for maybe glue dispensing for an XY axis, or for welding for using an XY axis for 2-dimensional motion along a certain path that was predefined. So in the IEC world, Yaskawa had really good camming functionality, and so we thought if we introduce, or if we are able to make the path in the form of a CAM file or a CAM path, then we could basically make use of the high resolution CAM calculation done at the motion kernel level to sort of get coordinated motion in the controller. So that was the motivation. So this we're not yet doing pure interpolated motion. What we're doing is basically using camming to do coordinated motion for XY axes. And this can be expanded to multiple axes. It can be expanded to gantry systems doing X prime, Y prime, and so on. So let's get started with the first of the three function blocks that we're going to talk about today. It's the path generator. The path generator basically is used to convert user-defined data points into CAM files, which can be used to produce coordinated motion. And these CAM files are preloaded for you in the motion engine using this function block. So the CAM files will be ready to use once you define your straight line or arc segment data types. For example, if you want to create a circle or a rectangle, a triangle, or an ellipse, you basically have to you have to give in the data into the path data type in the path generator with start endpoints and other details like angles, and the path generator will create CAM tables for you that are already pushed into the motion kernel ready for use. In this case, throughout this presentation, we'll be using examples where you have XY motion only. So the main output of this path generator function block, the main outputs are segment data, which basically gives you the details of the different segments that have been created, and also path ID for the CAM files that are created. The second function block we're going to talk about is move path, which uses the path ID that was created in the path generator and the details that were created in the segment data type, and it uses it to start a motion. And you can see here one of the inputs, or one of the var in-out data types in this function block is gantry, which basically means that you can use a virtual axis as a master to move the X and Y axes, or X prime, Y prime axes, and so on. Again, just a reminder, right now we have the capability for only X and Y, but you can most certainly add prime axes into the mix here. So the path ID that is generated from the path generator can be input into the move path, and the move path is like a move absolute or a move relative. It basically has motion embedded in it, basically has camming motion embedded in it, which will cause a virtual axis to move, and the X and Y axes that are cammed to the virtual master will start moving along the cam path that was created, and essentially it'll give you the motion or interpolated or coordinated motion that you desire. The third function block that we will be talking about is called calculate angles, and this basically is used to help generate profiles for arcs. The two methods in which you can create an arc are using a 2-coordinate and center point method, or using 2 coordinates and a radius method. So basically this function block will be used if you need to generate a path that follows an arc to create start and traversed angles for the path for the data that's required for the path generator. These are the two types of arc definitions that you can use. The first one, the one that you see on top, where you have x1, y1, x2, y2, and xc, yc, where you're defining 3 points for an arc, the start point, end point, and the center point. The other method is where you give it a start point, end point, and a radius. Once the definitions of the arc are given into the calculate angles function block, they can be used in the path generator function block to create your CAM profile. So let's look at the path generator in more detail here. On the right, what you see, the structured text that you see, that's basically the data type definition from the Gantry Toolbox that has been created for the path, for the path generator and for the move path. So essentially what you see there is the basic building block of this is a path structure, which basically contains information about the path that you're trying to create. And the different detail elements that you create for a path can be seen under that structure called path detail at the very top. It contains information about the segment. It contains information about the x coordinates, y coordinates, a radius in the case of an arc, start angle and a traversed angle for an arc, resolution if required, and also we have provision for providing outputs while the axes are moving along a certain path. And also it's got a master end parameter in it. Here's an example of how to create a straight line path. So what the structured text that you see here is basically from the Gantry data types file. To create a straight line that goes from 0, 0 to 10, 10, you basically have to define your data. And the variable that I use here is called vector path. And the first element of my vector path is my segment type, and it is a straight line. The second element that I define is my x coordinate, the endpoint, and the third element is the y coordinate endpoint. And we're assuming that the start point is 0, 0. So this is all you basically require for a straight line path generation. Resolution in this case is not important because as it's a straight line, and when you create a cam for a straight line, all the interpolation is done automatically in the motion kernel for you. Here's an example of an arc, and the coordinate system that we are using in this toolbox is basically the one that you see on the upper right corner, where 0 degrees is on the positive x-axis and positive 90 degrees is on the y-axis. And the positive traverse is basically counterclockwise. So the different data or the different variables that need to be defined for the path struct are segment type, first of all, that you see there. It's the arc. The second is a radius. Since it's an arc, you have to provide it with a radius. You do not have to provide an x coordinate or y coordinate for this. You also have to give it a start angle of 180 degrees. In this case, since we're starting from this point, this is the start point, so you're basically 180 degrees from your 0. So if you were here, you're 0, you're starting from this point, which is 180 degrees from 0. And then your traversed angle is basically the angle that is traversed from your start point. And since it's a negative 180, or you're going in a clockwise fashion, you're basically traversing negative 180 degrees. And then I give it a resolution of 0.05 since it's an arc, and I'm setting an output flag in this example here. Here's a third example where I have a combination of straight lines and arcs, and to define my first segment, which is a straight line that goes from 0, 0 to 0, 10. This is what I define for my path. The second segment is an arc, and here's my definition for that arc. It starts at 180 degrees and traverses minus 180 degrees. The third segment is a straight line that goes from 1, 10 to 1, 0. And this is my definition for that. And my fourth segment is again an arc that is clockwise. So my data that I enter is basically as shown here in the purple color. And also the last element of that path structure is the number of segments that I am using in my path, and that is 4. I'm using 4 segments, 2 straight line segments and 2 arc segments. So once this data is entered into the vector path variable, once a vector path variable has been populated with this data, I can execute my path generator, which will create a path ID and segment details from the path generator function block. And so you can see the kind of segment details that I get from my path generator function block. You can see here, by default, the first array is left 0. You start from array element 1, and you have 4 segments there. So it basically gives you all the details about what segment. First of all, you have the segment number, you have the output D word that has been set, and also the distance that the virtual master has to travel so that the first segment can be completed. Another output of path ID is basically the CAM table IDs that are given for the various axes in consideration here. You have 2 axes. We are looking at XY axes. You have a path ID of 1 and a path ID of 2, 1 for the x-axis and 2 for the y-axis. And also it gives you the path length, the total length that the virtual master has to travel, so that you get a combined motion, a combined profile of the racetrack that we just generated. The next function block here that we are going to talk about is the move path. 2 important elements that are input into the move path function block are the segment data or the segment details, the variables that we created using the path generator. So the segment data that comes out of the path generator is important, as is the path ID that comes from the path generator. So these 2 come in from the path generator. And the move path basically has cam ins, cam MC, y underscore cam in function blocks in it that basically help you generate the motion based on a virtual axis. So the virtual axis master, virtual axis basically moves from the point where it's at to a certain distance that is calculated with the path generator, and it also makes the x and y axes move along a certain path. And you can see here, this is the profile that was created for the racetrack kind of profile that we talked about earlier, where you had 2 straight lines and 2 arcs. And you can see the profiles of the velocities of the 2 axes. And also, we had set an output word for, maybe firing an output while the 2 axes are in motion. And that is the last plot that you see at the very bottom, the output flags that are getting generated. Now, based on the data that we used, if you plot the data in Excel, if you just take the actual positions of the x and y axes and plot it in Excel, this is what it looks like. So we had generated the variable called vector path for the for the motion along a racetrack, and this is what the Excel data looks like. And this is a top view with the x-axis and y-axis here. Start point, it moves along the path and comes back to where it started from. Here's a second example. This one comprises of just 1 arc, basically a 360-degree move, or a negative 360-degree move, where the circular path variable is defined in this fashion here. It's an arc of radius 0.5. It starts at 180 and traverses minus 360, and I have a resolution of 0.05. And basically the whole path consists only of 1 segment, which is a circle. It starts here and traverses negative 360 degrees. And once the path was created, or once the segment data and the path ID were generated, they are input into the move path function block, which, when that executes, takes it along a path as shown here. The x and y axes, positions, the individual velocities, and this is the top view of what is generated. The third function block we're going to talk about here is calculate angles. And we had briefly talked about what what the calculate angles function block can do. It basically makes use of, or this is basically used to create an arc. So if you have trouble in creating an arc, or are thinking about what, let's say you have information about 2 points and the radius of the arc, but you don't know the center point, then you don't have to do the math to create an algorithm that can generate an arc for you. With this calculate angles function blocks, you can either have data in the form of 2 points and a center point, like mode 0, and you can also have data in the form of 2 points and a radius, which is mode 1. So either way, you can create the data that's required by the path generator to create an arc. And also you can give the direction in which the arc should be made. So talking about mode 1, so if you have a radius, there are 2 points and an 2 points and a radius can create an arc like this, as shown in the blue line, or the blue arc. And it can also, with a different center point, you can also create 2 points and or with a center point, you can also create a different arc with the same radius, but with a different center point. And the difference here is the sign of the radii. So if you have a positive radius, you basically get the minor axis, or the minor arc. Or if you have a negative radius, you basically come up with a major arc, which is traversing 270 degrees, minus 270 degrees, basically, in this case. So you can see here with a positive radius, you start from 180 degree and traverse minus 90 degrees. And with a negative radius arc, with the same definition, you start from 270 degrees and end with a minus 270 degrees traversed angle. So this was just an explanation of the different modes in which you can enter data for an arc, to create an arc that can be given into the path generator, such that the path generator can create the adequate cam profile that can be fed into the move path function block. Here's an example of creating an arc with 2 coordinates and the radius. So you define your mode first, and then you give in your x1, y1, and x2, y2 points, and also provide the radius. So if with a negative radius, you basically end up with a major arc, or an arc that traverses more than an acute angle, and also provide the direction of travel. The other way of entering data for an arc to create the path for an arc is 2 coordinates and the center point. So you can generate you define your arc definition for defining your mode, which is basically 2 coordinates and a center point. Give it your x1, y1, x2, y2, and your center points, and also the direction to generate your start angle and traversed angle, which basically need to be used in the path generator for creating the path for this particular arc. Here's an example for a contour application. Basically, the calculate angles, where the inputs for the calculate angles basically tell you what needs to be input. In this case, you have a negative radius, and then you have your x1, y1, x2, y2 data in here. And so all these 4 colors represent the 4 paths that were created using the calculate angles inputting data into the path generator. I called it a flower path, the path that we just saw on the previous slide, and I used that to create a path. And once that was done, it was fed into a move path, and the move path basically created motion on my x and y axes, and this was how my motion looked like. And when I took the data, the actual positions, and plotted it out in Excel, this is how my results turned out to be. That is the end of the third and final presentation for today. I will open the floor up for questions, to answer questions if you have any. I think we already did receive a few comments and questions from on the chat window. We'll try to answer those questions one by one. is there a way to incorporate outputs into the path? Yes, there is an output on the output is on the move path function block. It's called output flags. That has to be defined when you're creating your path itself. When you create your path, you can define what outputs you need to turn on, and the data type is essentially a double word. You see here, when you define when you create your path, there is an option for that. So there is an output flags data type that is defined already in your in the Gantry Toolbox that can be used to turn on an output or turn off or on multiple outputs when you're moving along a path.
That's right. When we first created this function, we had just a Boolean there for one output to turn on or turn off, and we changed it to a 32-bit word to handle up to 32-bit or 32 outputs along the path, which should cover any possible scenario. There was another question, and as always, we will have this presentation available on our website for review afterward. It'll take us at least a week to get it recorded and cleaned up and finalized for that to be downloadable. And Nishant, could you explain where you specify the X and Y axis refs, the axis IDs?
Yeah, the X and Y axis IDs are basically specified as part of the Gantry Toolbox. So there are, I'm sorry, as part of the Gantry structure. If you look at the move path, function block, this is the function block that basically makes use of axes so that you can get motion. So one of the inputs into the move path, or one of the inouts into the move path function block, is this Gantry, which contains details for the axes, like axis ID. It's contained in the Gantry Toolbox. If you look at the Gantry Toolbox, it contains information about which axis is your x-axis, which axis is your y-axis. If you have prime axes, you can have those in there as well. So the definition is basically made in you can have your definition in your initialized POU, but they have to be defined in the form of a Gantry system.
So there was another question if we have videos of any of these patterns in action for demonstration purposes, and I don't think that we have any in our hands right now, but some may exist that we can get a hold of. And another question was pertaining to creating a complete sample project to run on the standard demo box, and yes, we can do that as well quite easily. A lot of these examples we created here for the webinar were done on a demo box, so that's an easy thing to finalize and to put on the website as well.
Here's where I defined my Gantry data type, or my Gantry variable, which contained information about which axes I was basically running. In this example, I was running only an X and Y axis, and I had my virtual master. So this was my definition for my X-axis, and this second line was my definition for the Y-axis. And axis 26 was my virtual master. And there was a question about whether there would be a sample program. Yes, we can definitely share the sample program along with the webinar.
There's also questions pertaining to the general direction of the toolboxes for the 2.0 release of MotionWorks IEC. And there has been some transition, and kind of because some of these blocks that Nishant discussed were really more new and more experimental than others. Thus far, we've had them out for over a year. We kind of realized we made them for one customer last year to begin with, and then there was a lot of requests for things like this that had come up over the past 9 months. And so we worked more and more with customers using the path generator and move path, probably a total of 4 times now in real applications. And so as part of that kind of back and forth and working with a couple accounts, we realized that it made more sense to have the move path and path generator in the Gantry Toolbox, because that's typically the kind of mechanism that these functions really pertain to. And so they were originally created in the CAM Toolbox, because they do use camming functions, but really the goal of the move path and path generation is to disguise the camming aspect of it and really make it cater to the XY interpolation motion path feature that it does try to provide. So that was the reason why those functions were converted over to Gantry Toolbox, and those should be updated on the website now, both version 8 for the 1.x Pro version of MotionWorks IEC, and also version 200, which is the first version we compiled for MotionWorks IEC 2.
There's a question about whether everything needs to be defined beforehand or whether it can be modified real time. You can modify your data real time. All you need to do is modify the data that you see here. Once it's modified, you can basically refire the path generator function block. Once you modify your data, you can basically refire the path generator function block, and that should give you a new path ID and new segment details. And then that can be used to be passed into your move path function block and get motion for your new path. So you can modify it on the fly.
Right. The question is asking about, can the path be modified at real time? And I kind of have a question as to what they mean by real time, because the path kind of has to be known before you begin moving the path for the cams to be calculated. So by real time, I guess we can do it in the controller and refire it, as you said, Nishant. But once the path has to be known before motion can begin, the way this is designed to work. So you can't change the path midstream once motion is started.
There's another question, if can you set X or Y axis as the master so the Y movement is a function of the X movement? I think for that kind of motion you really don't need this toolbox. You can basically make use of camming functionality to, if you set one axis, if you just have two axes and you just set one axis as the master and the other axis needs to undergo synchronized motion corresponding to the master's position, then you can basically make use of camming. This is one more layer where you want synchronized motion of two axes where the third axis is the master.
Right. This is really designed around getting two axes to work in unison as an XY gantry pair. And really there's kind of provisions in here to expand that if it were needed to be XYZ or some other set of interpolated axes.
Right, so if you look into the latest Gantry Toolbox that's available, we have made provision in the data type definition itself such that you basically have multiple axes now in the Gantry structure. You have a virtual axis, x-axis, y-axis, z-axis, and then you have the x prime, y prime, and z prime. So all this functionality can theoretically be scaled up to provide for up to 6 real axes and 1 virtual master.
That's right, but we don't have support for the prime axes incorporated yet.
Right.
There was another question asking for if examples of the CSV file transfer utility are available, and they are not yet available, but Greg will be making a sample project that's available from our website. We're basically making a DLL utility that simplifies the process of sending a file to the controller for use by a Visual Basic or C# project. Okay, I think there was one final question we see here, and someone has asked if it's possible to start, pause, and continue motion, and that is possible. The move path function block is basically running a move absolute, MC move absolute block on the virtual axis, which is the tool path itself. So you could refire the execute of move path with a different speed or a velocity of 0 and cause it to change speed and then continue by refiring the execute block. And I mentioned the DLL that we were talking about for sending files to the controller, and
What we have now works with frameworks.
.NET Framework, yes.
.NET framework. So with plain C#, you'd have to build up the HTTP. You'd have to build it up with a stream writer in C yourself, as opposed to using the web request method. You'd have to build up to transfer the packets over as a stream wrapped in the protocol. So I don't have a direct translation right now to C, because we're using the Microsoft frameworks.
The question is about the DLL, and is it going to be free to distribute? And I don't know 100% yet. We haven't discussed it here, but I'm guessing it will be. It's going to be a simple utility just to send the files. It shouldn't be too complex. It shouldn't be too much of a big thing to just offer that as a free tool for people to use. All right, if we've answered all your questions so far, we want to thank you for spending an hour with us this morning after a long weekend here in the U.S., and we look forward to discussing future IEC applications and features with you at the next webinar. So thanks everyone for joining with us.